Basic physics models often simplify the world by treating objects as ideal point masses. These are sizeless points that only move along linear paths. Real-world objects have physical dimensions and mass distributed across their volume. They don't just slide, they spin, roll, and pivot. We define pure translation as a state where every particle in a body moves with the exact same velocity at any given instant. Pure rotation is different. Here, every particle in the body describes a circle centered on a common line. To analyze this, we focus on a specific constraint, the rigid body rotating around a perfectly fixed axis. This means the distance between any two particles in the object never changes. By fixing the axis, we reduce the motion to a single degree of freedom. The complex behavior of an extended body becomes a one-dimensional calculation. When an object rotates without leaving its location, we cannot use linear meters to track how far it has moved. Instead, we measure the angle swept by a point on the body relative to a fixed reference line in its plane of motion. This angle, theta, is the angular displacement. It represents the position of the entire rigid body at any moment. We measure this change from an initial displacement, theta 0, established at the start of our observation. The time rate of change of this displacement is the angular velocity, omega. In a rigid body, every particle shares this same angular velocity at any given instant. If that rotational speed changes, we measure the rate of that change as angular acceleration, or alpha. Together, angular displacement, velocity, and acceleration provide the variables necessary to describe any fixed axis rotation with mathematical precision. In linear physics, we use standard kinematic equations to relate velocity, acceleration, and time, such as the formula final velocity equals initial velocity plus acceleration times time. These equations only apply when acceleration is constant. Rotational kinematics follows this exact same rule for angular acceleration. Because the relationship between the variables is identical, we can map them directly. Linear displacement becomes angular displacement. Linear velocity becomes angular velocity, and linear acceleration becomes angular acceleration. By swapping these variables, we translate our linear equations into a rotational framework. This first equation allows us to calculate the final angular velocity of a body if we know its starting speed and constant acceleration rate. We can do the same to find total angular displacement over time. This third translation provides a way to solve for rotation even when the time variable is missing. These equations demonstrate that the mathematical logic of motion remains consistent whether an object moves in a straight line or around a fixed point. This consistency exists because both sets of equations are derived through the same calculus principles. We start with the definition of constant angular acceleration. Alpha equals the derivative of angular velocity with respect to time. By integrating this constant acceleration over time, we find the change in angular velocity. This integration results in our first equation, omega equals alpha t plus the initial angular velocity. Integrating a second time allows us to find the total angular displacement. The area under the velocity curve produces the parabolic relationship seen in the displacement equation. These rotational formulas are not just analogies, they are the direct result of applying integral calculus to a fixed circular path. To see these equations in action, consider a motor wheel that increases its speed from 1200 RPM to 3120 RPM in 16 seconds. We can use our framework to determine the exact acceleration of this flywheel. Our first objective is to calculate the uniform angular acceleration. First, we must convert revolutions per minute into radians per second. A radian is the standard unit of angular measure, representing the angle where the arc length equals the radius. We multiply 1200 revolutions by 2 pi radians per revolution and divide by 60 seconds. This gives us an initial velocity of 40 pi radians per second. Using the same process for our final speed of 3120 RPM gives us 104 pi radians per second. By dividing the total change in velocity by the 16-second interval, we find an angular acceleration of 4 pi radians per second squared. Converting raw mechanical data into standardized units allows us to apply theoretical kinematics to real-world hardware. Apply our second translated equation to find the total angular displacement, theta. After substituting our values for initial speed, time, and acceleration, The math shows a total displacement of 1,152 pi radians. To make this result practical for an engineer, we convert these radians back into revolutions. Dividing by 2 pi radians per revolution shows that the wheel completed 576 full rotations during those 16 seconds. By mapping a rotating wheel to linear principles, we were able to predict its physical behavior with absolute accuracy. Rotational kinematics is the mathematical projection of linear motion onto a fixed axis, providing a consistent framework for any system spinning around a stable center.